maybe I will just start now. It's okay to start?
Yes, you can start.
Okay, I will start. We had started to talk about fields and field extensions. So at the end, I got slightly ahead of myself because I started to talk about splitting fields, and I want to continue with that a little bit later. I will first talk a little bit more about algebraic extensions. So I had told you about finite extensions and algebraic extensions, and now I wanted to first show that finite field extensions are algebraic, and also there's a converse. Because, a priori, it's not obvious that if you have an extension which you obtain by just adding one algebraic element, that would be, for instance, algebraic, because the requirement to be algebraic is that every element in the bigger field is algebraic over the smaller, but it's actually quite easy to see. So let me say this. We have the following proposition. So L over K, the finite field extension, then algebraic field extension. This is actually quite simple. It's similar what we already did when we were looking at simple algebraic extensions. So proof, take any element in L, and we can just look at, so say, first say that M of L over K, then we know that M plus 1 elements will be, in L, will be linearly dependent over K. So we can just take, for any element A in L, we just take 1, A, and so on until A to the M are linearly dependent because the degree of the field extension is the dimension as a vector space. And so thus, that means M in K not all 0, such that sum I equals 0 M bi a to the I, a to the I is equal to 0. And so this is just a polynomial which vanishes at A. X to the I. X, and it's not 0. Okay, so that's very simple. Also, okay, so, and conversely, mark if L is equal to K, A1 to M, and A1 to AM are algebraic over K, then it follows that L over K finite extension. And as you can see, this is easy induction. So K 1 L for some L between 0 and M is equal to A1 to minus 1 L to it, this simple algebraic extension. So that means that the degree of the minimal polynomial of AL over KA1, so of the minimal polynomial of AL over finite. So the degree of the for all L between so and so we just have induction. By the degree theorem, the total degree of the extension is the product of these numbers, and all of them are finite. So we want also to see, so let's just look at some important. If we have a field extension, we can look at the elements in the bigger field which are algebraic over the smaller one. This will always be a subfield. Let M set of all elements in the bigger field which are algebraic over the field over the smaller. And algebraic field extension. Field, K is a subfield. Basically, you only have to show that M is a field. So clearly, K is contained in M. The element is algebraic of a field is algebraic over the same field. And if A and B are elements in M, then if I look at the field extension KAB, this is a finite field extension because I've added two algebraic elements. Finite. So all elements in it are algebraic. So thus, whatever A plus B, A minus lie in M. Now they lie in KAB, and so therefore they lie in M. And so it follows that with any two elements also lie in M, and so it follows that M is a field. Contains K, as I said, and by definition, M over K is an algebraic field extension because we have precisely required that every element of it is algebraic over K. So an example of this of algebraic numbers, so Q bar, set of all complex numbers such that algebraic over Q. So this is so all complex numbers which are zeros of polynomial equation with coefficients in Q, and by definition this is an algebraic extension. But obviously an infinite algebraic extension. As I said, it's called algebraic numbers. So in a moment we'll see that this is the so-called algebraic closure of Q. So C itself is algebraically closed. That's the fundamental. Anyway. So this is this thing. Come to this algebraic closure in a moment. So we also obviously want that if we make composition of algebraic extensions, it's also an algebraic extension. So corollary algebraic extension, but for any algebraic extension. So let L over M over K, algebraic field extensions. Then L over K is also an algebraic field extension. Note this is not completely trivial, because we say that here every element in L is supposed to be a zero of a polynomial with coefficients in M, and every element in M is supposed to be a zero of a polynomial with coefficients in K. To deduce from that that every element in L is also zero of a polynomial with coefficients in K is not completely obvious. But it's quite simple by using, again, that relation of being algebraic and finite. So we take any element U in L. So note if these two were both finite field extensions, then this extension would be finite and therefore also algebraic, but we precisely assume it's not finite. But we can still reduce ourselves to the finite case. We want to show algebraic over K. So we know that U is algebraic over M. So we write out what this means. So that means there exists a polynomial G, right, as say some I equal 0 M AI x to the I M, which is not 0, such that G of U. Now, the trick now is, instead of, in order to talk about the algebraicity of U over K, we don't need to know everything about everything that happens in M. We only need to deal with these coefficients AI. And if we put all these together, we end up in a finite field extension. So we put N, so another field extension, to be K, to which we add A1. So then each of these elements is algebraic, and we add finitely many of them. So this is a finite algebraic extension of K. And we see that u is a zero of a polynomial with coefficients in n, because, these are these AI. So, and u is algebraic n. So thus, nu over n is a finite algebraic extension. Finite extension, because it's an algebraic extension generated by just one element. So thus, we see that if we take the degree of k, this is the degree of nu over n times the degree of n over k. And these are both finite, so this is finite. So the degree of nu over k is finite, so it follows that every element of nu is algebraic over k. In particular, u is algebraic over k. So, okay, so that's that. We are not going to use this much, but it's useful to. So, this part of the course is on Galois theory. This is to start to study field extensions via the so-called Galois groups, which is the automorphism of the smaller field over the bigger field. So. Field homomorphism. So, in Galois theory, we study extensions L over K via of K automorphisms of L. So obviously, in order to do that, we have to be able to understand something about these K automorphisms of L. In particular, we want, so more generally, we can, so let's first look at this in the case of simple algebraic extensions. So we would be looking at study of K automorphism, I recall to you, is an automorphism of Ka, which is the identity on K. So more generally, also partially because we needed to study this, we could more generally study the following. Instead of just taking K automorphisms, which are automorphisms of Ka, which are the identity on K, we could say we give ourselves a homomorphism, an isomorphism of phi to some other field, and we look at isomorphisms of fields which extend this isomorphism. So the case of K automorphisms are then automorphisms of the bigger field which extend the identity on K. So we want to study these extensions, and the most important case, however, is the K automorphisms. So let me define this. Get K, so prime, isomorphism of fields. And we take field extensions, so let L K and L prime over K prime. So an isomorphism say large phi L to L prime is called an extension of our original phi. If I restrict phi to small k, which is a subfield of L, it goes to k prime and just becomes, so if I restrict the large phi to k, then it maps to k prime, it actually just becomes phi. If phi, large phi, restricted to k, is equal to small phi from k. Okay, and now we want to study. So as I said, the most important case are the K automorphisms. L, which means in this definition, we have that L is equal to L prime, K is equal to K prime, and phi is the identity of K. Okay, now let's look at this case. So maybe, okay, I go back. Now we want to prove such extension to say what the extensions are in case simple algebraic extensions. They will have something to do with the minimal polynomial. So let's see. So first, I make the following obvious remark. So if prime is a field isomorphism, then we get an isomorphism of rings, then get ring isomorphism. I could call phi star from kx of x by just sending a polynomial sum I equals 0 to n x to the I just apply phi to the coefficients. Clearly is an isomorphism of rings. Then theorem for algebraic extensions. So let so and say L over K field extensions. Let A L be algebraic over K with minimal polynomial and we take A prime 0 in L prime of the kind of transformed by phi minimal polynomial. So let A prime be a 0 of how did I call it? Phi star. No, I just apply to the coefficients of the minimal polynomial this phi. Then there exists extension from extension which stands A is equal to A. So that means we have complete understanding of the extensions of this phi to this simple, the corresponding simple algebraic extensions like that. We know there exists such an extension for every other zeros in this of this polynomial in this phi, in L prime. No, I wrote it, but anyway. And there exists one, and it is unique. There's precisely one. The most important case, as I said, is that K is equal to K prime and L is equal to L prime. So I write it out. So we mark most important case. Is when K equal to K prime, L is equal to L prime, and small phi is the identity on K. Then it says, then the theorem says so for every zero A prime of Fa in L, there exists K automorphism of L No. There exists a K isomorphism. Large phi from K of A to K of A prime with I didn't repeat the common part, so maybe I should have. So assume we have this. So that means, so we assume that, so maybe I write it here. A in L, algebraic. Fa over K. So that means, so if we have, we are in the situation, we have L over K is a field extension, A in L is algebraic with minimal polynomial Fa, then for every other zero, or possibly the same zero, but that would be the identity, for every possibly different zero, A prime of Fa in L, there exists a unique K isomorphism from Ka to K of A prime, which sends A to A prime. So we know precisely what these K isomorphisms are, just in terms of the minimal polynomial. Now, this will turn out to be very useful in proofs. I mean, a very useful statement. Most of the time one uses this version, but in some proofs one actually needs this. So that's why I stated in this generality, although it is rather long to state and slightly confusing. Proof is actually quite simple. Start with the easy part, which is the uniqueness. It's easy to see that these are determined by what I wrote there. So let our given phi we have to see there's only one, we can precisely say what it is. And so in particular, it is unique. So we just have to remember where we are. We note that we know very well how a simple algebraic extension looks like. So Ka can be written as the set of all G of A, with coefficients in K, and K prime of A prime can be written as not the derivative, it's just another polynomial, G prime, where G prime is an element K prime of X. No, that we know. So now assume we have given such a phi. So let such an extension as above. Then what can we say? So if I take phi, if I take any element in Ka, I can write it as phi of A for some polynomial. So we get phi of what? Well, if I write maybe I first write it. So write for and say bi x to the I in Kx, get that of G of A phi of some I equals 0 to n bi. And now phi is a field homomorphism, so it is compatible with sum and products, and it extends the small phi on K. So this is the same as sum I equals 0 to n phi of I phi of AI. And now we know that phi bi is an element of small k, so this just becomes small phi of bi, and this pulls out. So this is phi of A is A prime, so this is some I equals 0. I, which according to the notation I introduced here is just star of G prime. So I have just explicitly written down what phi does to any element Ka. You just apply this transformation to, you write it in this form, and then you do. This is not enough for the existence, because a priori we wouldn't know that this is well defined. You can write an element in Ka in many ways as some polynomial. So we have to prove the existence. Well, obviously, the existence we do by writing this down. We have found the uniqueness. That's why one usually proves uniqueness first. Once you have that, you know what the thing should be, and then you have to show that it does it. So we define from Ke prime of A prime by sending element G of A for G a polynomial to P star. The only choice we have, because we have seen this, it's determined to be this. Yeah, so then the main thing we have to see is that P is well defined. We know that Ka A. So we have to see that if now G is lies in, so thus we have to see element. So if I have two elements which, if two elements here give the, two polynomials give the same element here, then the difference is a multiple of Fa. And so then we should still get the same on the other side. Okay, but so if that's the same, that GA, but maybe I could also say it, you can say it less complicated. So, I mean, it's the same, but I think it's nicer. So if 1 of A, so the well-defined line, is if G1 of A is equal to G2 of A, we have to show star 1 of A prime is equal to so, but this means that G1 minus G2 of A is equal to 0. And then we have to show star of G1 minus G2 prime is also equal to 0 to get the well-defined. Okay. Well, so if the G1 0, then it follows that G1 minus G2 is divisible. So maybe I just say that FA divides G1 minus G2. Because we know that FA is the minimum polynomial. It divides every polynomial which vanishes at A. Generator of the ideal of all the polynomials which vanish at A, which is the same. And so it follows, because we have a homomorphism, that phi star of FA divides phi star of G1 minus phi star of G2, which is the same as phi star of G1 minus. And so, obviously, phi star of FA vanishes at A prime, so also this vanishes at A prime. Okay, so this is this, so it's well defined. So as a non-zero homomorphism of fields, phi is obviously injective. Because it's a non-zero homomorphism because it extends an isomorphism, and we know that the kernel of the field homomorphism is 0, or the whole of the field. And as star is an isomorphism, star here from k of x to k of x is an isomorphism, so it means we reach, therefore, if we have all g's here, we get all g primes, so that means the map is surjective. Also surjective. That's an isomorphism. And clearly, if we take phi of A, I can write A as the polynomial x evaluated at A. Yeah? And so, according to our definition, this is star of x, but the coefficient is still 1 of A prime, so this is A prime. And so it sends A to A prime. Okay, so this was this statement. I want to make a, so it's, as I said, it's maybe not so clear to you why one should care about such a statement, but it turns out to be very important. It's one of the tools that we use all the time. So one has to also get somewhat familiar with it. In particular, as I said, the remark, but it's just field extensions to finite, to simple algebraic extensions, extensions of homomorphisms to simple algebraic extensions one will want to use all the time, and they are very useful for studying field extensions. And so now I leave it out. I want to make a few remarks just for completeness about algebraic closure, and then we splitting fields. So just without proof, I want to briefly say that every field is algebraic closure and that it's essentially unique. So what does it mean? Definition called algebraically closed if every non-constant polynomial has a zero with coefficient in the field has a zero in the same field, or equivalently if every polynomial splits into linear factors. And then, so let me L is called algebraically closed. One of the following two statements hold, which are equivalent. First, every polynomial f with coefficients in L so every non-constant polynomial f in Lx has a zero in L. The equivalent statement is that every polynomial splits into linear factors. Every L f in Lx splits into linear factors by which I mean the following. We can write f as a some constant b x minus a1 times n is equal to f and b. So that means, in other words, all the zeros of f are in L. That means the field is algebraically closed if we can solve every algebraic equation given by a polynomial, just staying inside L. So let's see. So why are these equivalent? It's kind of clear. So 2 plus 1 is essentially trivial. The other one is induction. So if A is 0 of f in Lx, minus a divides f, we can write that f and now we make induction on the degree of f. Okay, so as examples, we know some fields. So are not algebraically closed. Many polynomials coefficients in Q which don't have zeros in Q, whatever x squared minus 2. Here you can take, for instance, x squared plus 1, which doesn't have a 0 in R. But some are algebraically closed. C is algebraically closed. Often called the fundamental theorem of algebra, although it is not really a theorem of algebra. And any course first course on complex analysis. I expect you have seen it or will see it soon. And then another example which we have just seen is that Q bar is algebraically closed. For that Q bar, the field of algebraic numbers was the set of all elements in C, which are algebraic over Q. And you can prove as an exercise that this will be algebraically closed. So now we want to talk about the algebraic closure. So the algebraic closure of a field is a field which contains our given field as a subfield, such that the bigger field is algebraically closed. But you want the bigger field to be as small as possible. And actually, the way you can do this is to require that the bigger field is algebraic over the smaller field. Field extension called an algebraic closure L is algebraically closed. And L over K. Right. Every element of L is a zero polynomial with coefficient in K. So this I will not prove, but every field has an also so field. Every field has an algebraic closure, and two such algebraic closures will be isomorphic, I mean K isomorphic. So I'm not going to prove it. The proof application of Zorn's lemma. So Zorn's lemma is one version of the axiom of choice. One uses it, for instance, to prove that every vector space has a basis. And a rather similar proof, basically, in some sense, the same proof, will also prove that every field has an algebraic closure. I mean, it's a similar kind of argument. Okay. So we have one example of an algebraic closure. This is Q bar, algebraic closure of Q. So that follows. We know that Q bar is algebraic over Q by definition, and I have claimed here it's algebraically closed, and that means it is a closure of Q. Okay, so much for this. So now we come back to our splitting fields. So somehow similar, only for one polynomial. So if I have a polynomial with coefficients in the field k, the splitting field will be the smallest extension of k over which this polynomial splits into linear factors. I had already briefly introduced this. I will study it a bit more. Okay. F is x a non-constant polynomial. So we want to study a field where it splits into linear factors. The smallest field So I said first we want to find the field extension over which f has a 0, and I had this theorem which I already proved. So let f in kx say be an polynomial. Algebraic extension L over k, maybe so of degree L over k equal to the degree of f, such that f has a 0 in the bigger field. Okay, so this we proved the last time. It was quite simple. Now we just defined L as kx modulo the ideal generated by f. Then it did it. So a corollary, easy corollary is that any polynomial n then there exists a field extension of degree at most n such that f has a 0 in the bigger field of degree Here, we can just apply the previous theorem to any irreducible. So maybe I should take a non-Cauchy polynomial, though. Yeah, of degree n. So just theorem any factor of f. So we can produce 1 0 of our polynomial. So then we can just iterate until we have as many zeros so that it splits. And this will finally give us eventually a splitting field. Now define the splitting field, and it's then clear how we get it. So definition. So let f in kx positive. A finite extension is called a splitting field of f over k if first f splits over L into linear factors, okay, but that is kind of okay, we can certainly do that, but for that we could even take the algebraic closure of K. No, that would do it for all. We want that the field is as small as possible. The smallest possible extension of K such that this works. So secondly, f does not split over any intermediate field. Except obviously smallest field over which it splits. Splitting fields are not, well, we'll see in a moment. So now we want to see that these things exist. Following corollary to what we just did before. F in x First statement, if I have an extension over which it splits, then I can get the splitting field from that. So let L over K extension such that F can be written as P of X minus 1 times and so on N with B and A1 in L. Then I can obtain the splitting field by just adding A1 to AN to K. F. Okay. Note I don't need the B because it is clear from the definition that B actually must already lie in K, because B is just the coefficient of F of X to the N. Okay, so the B plays no role here. And this statement is so my first, maybe this is the first statement, and second, L, and of L over K is smaller or equal to N factorial. And third statement is some other easy fact. So if I have a splitting field, of a polynomial F, I take any intermediate field. Extension. Then F is also a splitting field of this polynomial, small f, over L. So most of these are all somehow trivialities. I can briefly go through them. Just is what the definitions tell us. So first to 1. So clearly, our polynomial f splits over Ka1 to An, because we can see all at 0. I have to see that it does not split over any intermediate field smaller than Ka1 to An. That f contain in Ka1 subfield such that F splits large F. So then obviously we have that F is equal to, say, x minus C1 times but it's also this. So, you know, F. So thus it follows that if I put, for instance, AI into F, 0 is equal to F of AI is equal to AI minus C1 until AI minus Cn, and somewhere in the middle it will be AI minus AI. It will always be 0 for all I. From 1 to n. So it follows that each Ci, so it follows that AI is equal to so that means that 1 to n is contained in n. And so as K1 to An is the smallest field containing K and A1 to NF, it follows. So that means that splitting field. Okay. Now the other two statements are here we make an obvious induction. So by the corollary that exists the field extension, say L1 over K, 1 over K smaller equal to n, such that F has a 0. AI L, thus put you can write F equals x minus A1 times G degree smaller equal to n minus 1. By induction, so it follows that x is so over the degree. It follows that there exists a field extension L over K of degree smaller equal to n factorial, such that F splits over L. And now we know that a subfield of that will be the splitting field. So the degree of that will be smaller or equal. So now apply part 1. get the splitting field of degree. And the third statement is topology, but it's for some reason quite useful. I mean, quite explicitly stated. It's just if one remembers the meaning of the word, it's obvious. So we have here F is the splitting field of F in Kx over K, and I take an intermediate field, then F is also a splitting field of F over this intermediate field. So F splits. First, obviously, F is also an element in Lx. So K is contained in L. F splits F, because that's what we have asked, and it does not. Well, that's the definition of the splitting field. It does not split over any intermediate field of F over L because it's a splitting field of small f over k. So it doesn't even split over any intermediate field between F and K. So thus, such F is F. As I said, this is a tautology, but it's useful to know. Okay. Now I give a couple of examples of splitting fields, and then we're running out of time. Take, say, Q. Of the polynomial x squared. So this is clearly over. We have here the splitting x minus square root of 2 times x plus square root of 2, splitting of this polynomial into linear factors. And obviously, this polynomial doesn't split over any intermediate field because square root of 2 does not lie in Q. More generally, I have a polynomial of degree 2, so if f in x of degree 2 and alpha in L is 0 of f, then K alpha is of f over. No, because if I have this, I can divide my polynomial f by x minus alpha, and I get a polynomial of degree 1, which certainly has a 0. And so this polynomial f splits over k alpha into linear factors, and it cannot be cannot split over intermediate field because the only smaller intermediate field is k itself, and alpha cannot be in k because otherwise f would have a linear factor. Okay, let's look at what is the splitting field. Some polynomial of degree 3. So just x squared, x to the 3 minus. So, for instance, over third root of 2, we have that polynomial s is 0. But it does not split into linear factors. You can see easily that any other 0, for instance, over the complex numbers of this polynomial, cannot be real. And so, in particular, it doesn't lie here. So, on the other hand, we can take, but theta equal to e to the 2 by I divided by 3 in the complex numbers, zeros of f. Complex numbers are square root of 2 theta times the square root of 2 squared times the square root of 2. All are zeros, and they are the product of x minus square root of 2 times its own. They get just so this gives us the splitting. So no squared minus 2 x minus square root of 2 square root of 2. I don't know why I always write square root. Okay. So this is okay, and so it follows third root of 2 and theta third root of 2 is a splitting field of squared x to the third minus. So the point is here that you can obviously, it's easy to see that this is equal to q third root of 2 third root of 2 theta third root of 2 times theta squared, because you get theta here by dividing the second by the first, and on the other hand, if you have these two, you'll have these three below. And we know that if it splits over a field, then the splitting field is the one which is obtained by joining to the ground fields just the roots of the polynomial. And this is what we're doing here. So this is the splitting field. And we note that this field extension has 6. Which is 3 factorial. We have q three. So the degree of the field, and this is because the polynomial is theta squared. So squared plus theta plus 1. Because the third root of unity. So this means the degree of the field extension is at most 2, but we also know that theta does not lie even in the real numbers, so the degree of this field extension must be at least 2, and so it's 2. So it follows that q third root of the splitting field is 6, which is 3 factorial, which according to our previous corollary is the maximal possible. And so for completeness, I give the last example. So polynomial x to the 4 plus 1 over q. Let's take alpha any 0 in an extension. L of q. So for instance, the complex numbers, we could take alpha to be square root of I, so I divided 4. So then we see minus alpha, 1 over alpha, minus 1 over alpha are zeros of this f. Yeah, you see this immediately. If you replace x by here, if alpha is a 0, then minus alpha is also 0. 1 over alpha will also be a 0, and minus 1 over alpha. So, and it's easy to see, and these are all distinct. So thus, get that Q alpha is a splitting field of F over and so I didn't prove it, but this x squared plus 4 is irreducible. So the degree of the field extension is indeed 4. So we find that the splitting field of this irreducible polynomial of degree 4 actually has degree 4. Now in this case, we had before, if we have an irreducible polynomial of degree 4, we know that the degree of the splitting field is at most 4 factorial, which is 12. So in this case, it's much smaller. So somehow it depends on how big the splitting field is, and what it looks like depends very much on what this polynomial is and what its special properties are. Okay, so maybe that's as much as I wanted to say now. So yeah, so I will, are there any questions or comments? I will most likely arrange sometime later, either on Friday or early next week, to again meet on Zoom, as you are always sitting. So if you like, you can meet me. I will give you the information then, and you can talk to me about how you feel, or any kind of problems that have come up in the meantime, or questions that you have also about things different from the courses. Okay, so otherwise, for now, I wish you a good evening, and I'll see you for this meeting, and otherwise next week.
Okay, thank you.